Our next speaker is Dr. Phillip Alvelda. He is a scientist, engineer, serial entrepreneur, and educator. And until March 2017, he was a program manager in DARPA's Biological Technologies Office. At DARPA, he developed programs to take the latest neural engineering science and technology out of the lab and seed the creation of new mind-enabled industries. After leaving DARPA, Phillip started a company called Cortical, which he's going to describe to you right now. Welcome, Phillip.
Thank you, Lisa. It's always a pleasure to come back. I was telling Lisa just as the intermission was ending that every one of these conferences that I've been to, I've always found several gems. And so even though it's not a giant conference, very well curated. So it's an honor to be back. Thank you, Lisa. Some of you who might remember my presentation from last year's conference may remember that it was about the neural engineering program that I started while I was at DARPA. Really a fantastic experience. If any of you are considering a stint serving your country through that sort of agency, it gives you a perspective of what's possible in the world and who is doing things that you never get exposed to through any other venue. So I can strongly recommend the experience. But today I'm going to go a little bit beyond what the DARPA efforts started. And I'd like to give you a taste of even the things that you think are related purely to biological technologies and creating new industries around neural interfaces might have even broader impacts than you imagine at the first glance. And today in particular, I'm going to be talking to you about how what we have learned through the process of interfacing artificial intelligences to real intelligences with the aim of exposing and understanding and interfacing with what the brain is actually computing. So figuring out what those codes were and understanding how can you write in and out of the brain with high-density information, and how that has pointed to specific new directions in artificial intelligence. And in a way, I've come to think of it as how can you use the lessons of biological computing architecture, the wetware, to inform what you could do to artificial or synthetic systems to make them more capable, more anthropomorphic. So what I'd like to build is artificial systems that are more intelligent and less artificial with that inspiration. So that's what I'm here to tell you about. Now, for the DARPA background, for those of you who weren't here last year, the program I started really was to take the latest electronics and photonics technology and build fully implantable interfaces that would work at very, very high performance levels. So thinking of the mega neuron channel scale. Very, very high temporal resolution, so that you could begin to translate information in and out of the brain at information densities that are relative to complicated things. So not just getting a pulse rate or an activity or a health measure in low dimensionality. And even those wondrous things that DARPA had done to control a robot arm, that was kind of like 6 degrees of freedom, where we could control a data stream with kilobits of information. But if you want to think about the future of telecommunications, the future of media, and what that might look like with a brain interface, you need kind of much, much higher information densities. I'd like to be able to write HD video into the frame buffer that's in your head, your visual cortex. I'd like to be able to sense what you are intending to speak and translate that in and out of the body. And so that was the motivator for this program. So I can give you a quick report. Since that has happened, this is some of the work that I showed last year from right here at Stanford, Mark Schnitzer's laboratory, where imagine the old sensors of neural interface where you had a Utah array with 100 wires that was pressed into a couple millimeters of cortex. That was 100 wires. This is a system which optically is looking at the entire brain of a freely moving, awake rodent, where we are distinctly imaging and sampling information from over 1.5 million neurons in parallel. So, this is what I love about DARPA. You give a program announcement, you say, I want to read from 1 million neurons. 3/4 of the people say, you're crazy, it will never happen. And within 3 months, you've got performers like Dr. Schnitzer here at Stanford who deliver beyond your wildest dreams. And so you can zoom in a little bit and kind of get a higher resolution where you can see the flashing of the individual neurons. And keep in mind, this is looking at the entire computing surface of the cortex. It gives us an instrument to start decomposing what the signals, the language, the computational information content of that process might be. You add a little bit of information and image processing, and some AI to start doing the correlations, and you can look from the very sensory stimulus at the back of the brain where the visual cortex takes the information in, all the way through the processing and the condensation of that information into objects and deeper information, up to the decision sensors, decision operators in the forward part of the brain, the things that then actuate the muscles and control the mouse. We can see the whole chain with unprecedented precision. And of course, we aspire to put this in people so that we can see that level of acuity, looking at millions of neurons on the couple square centimeter scale so that we can expose the richness of our cognitive processes. Now, what I can tell you is that the technology itself, just in less than a year since the program started, has made wondrous advances. And you can see, this is just one to give you an example of the work by Rice University on the J.B. Pierce effort that's building a sensor. You can see in this tiny little area here, it's a piece of thinned silicon with a combination of laser emitters to excite and stimulate and create activity, but a new type of super efficient flat microscope that is so thin that it can be sandwiched between in fact, thin to the point where it's kind of flexible like a piece of tissue paper and conforms to the very surface of the skull. And the resolution that you see here, this is looking at in vivo bioluminescence. These are Hydra examples that have been stimulated with a glowing enzyme similar to like a firefly. But the point is, we now have technologies where we can watch the brain activity, generate photons, sense them directly in the sensor at 100-micron resolution in something that takes no volume that we can just instrument within the skull. And it includes all of the telemetry and wireless power reception that you need to be able to manage a two-way interface of that sort. So those technologies have advanced unbelievably rapidly. So now the question becomes, yes, we can see the neurons, we can look at what the computational processes are, and we can begin decomposing what are the elemental computations and that language of processing in the human brain. But what would we use it for? And is this whole idea of having one of these sensors in my brain and maybe having one in yours, and me being able to look at something and you be able to see this, is this fantasy? Well, we now have some inspiration that this is not just fantasy. And the verification and the proof of the possibility came from a rather unexpected quarter. This is a pair of conjoined twins, actually it's one set of twins, right? Where they actually have two independent brains that are inside one skull. But they're connected. And the fascinating thing is with this connection between their two brains, they can share senses, they can control each other's limbs, they can actually communicate to each other silently without anyone hearing, just through this connection. So,
I'm gonna do this for Krista first. Krista, gonna shut your eyes.
I could have never imagined, they were going to do anything that they can do now. There's nobody in the world that's connected the same way that they are.
I'm gonna touch somewhere on Sissy. You gotta tell me where it is, okay? Yep. Now where? Very good.
Due to their connection, they're able to feel what the other child feels.
Doing what we normally do with them, just seeing what sensories are actually still working and active and just having a bit of fun. Now where am I touching?
Oh, yeah.
Very good. Now where am I touching?
On her nose.
Very good.
They're even able to see through each other's eyes.
What color is it?
Purple and white.
Oh, you got purple. It actually takes a lot more effort for them to see things through each other's eyes than it does to feel things. Okay.
A bat.
No,
Gambler.
can't see it. And Taddy, can you tell me what color this is?
Pink.
Very good.
So, there's actually an hour-long documentary on CBC. I encourage you to go watch it. But the remarkable thing is when you start to look at what's inside the skull, it turns out that this is a cross-section of the two brains, and you can see this bridge between the thalamus. And that means that this channel, and it looks like it's about a couple million neurons in total, a bridge between two thalamuses with a 2 million channel bridge can convey the semantic information of muscle control, sensory information, feelings, whether they're happy or sad, presence, abstractions, all of it can be transmitted via this channel. And so the really interesting thing is, of course, this is happening, and this is a motivation. And when we're developing the technologies at DARPA and funding the different strategies for implanting devices in the brain, we're developing things that don't just lie on the surface of the brain, but can penetrate without doing damage, be embedded entirely within the brain in those areas where those types of interfaces we know work. Doesn't mean other interfaces are impossible elsewhere, but they've not been tried. But complete proof of concept, right there. Now, what else could we do with it? Obviously, we can build whole new industries, and of course, I feel like, okay, I did that at DARPA, got that industry started. They're going. Elon's putting $800 million behind Neuralink. Facebook is doing the mental typewriter. GlaxoSmithKline and Google are doing Galvani for the electromedicine. So all of these things are related to DARPA efforts that we funded and catalyzed, got the researchers to realize that, oh my God, if we put your electronics with my photonics and his neuroscience, we could actually make some of these things happen. And then, exactly as DARPA is so good at doing, we hold the workshops and we get all the community together, and then magic happens when the universities and the companies take up the torch and go and do great things. But this was a little bit of an unexpected direction, where we started to think, all right, now that we're starting to piece apart what is the code, what is the information embedded within these communications, how could they be employed not just to make an interface from a biological brain to an artificial system, but how could you use those ideas, those principles, the new things that we learned about what the brain was doing that doesn't yet appear in our synthetic systems to do much more powerful artificial intelligence? So today, of course, convolutional networks, deep learning, these are kind of the buzzwords. They're the tools that have become widely available, and all of today's industries that are kind of liking to be at the forefront of their markets, they're investing very, very heavily to say, we've got a business, we've got a lot of data, we've got an analytic department, but maybe let's use some of the new AI tools and we can superpower the business. We're trying to think of what are the new transformational things that would really advance what AI could do to not just create better businesses as we're operating them today, but to create entirely new types of business. And so the type of questions we ask are, as we understand the coding, you think the visual information comes into the brain in the back, just the raw inputs from the retina. And then as it proceeds forward in the brain, more towards the cognitive areas, the agglomeration and the synthesis of that information is combined to make ever more complex representations in the brain until in the frontal cortex you're making decisions about more complicated synthesis of all these different activities and stimuli, all kind of correlated and assembled into more complex kind of representations. But we're really starting to realize that the difference between the way our brain is organized in a mature adult is very different than the way a deep learning network represents a tiny little portion of the brain. And I kind of jokingly will say, our current deep learning networks are kind of prepubescent, not quite adult versions of a mini brain. And the title is kind of a little bit of a mouthful, but it basically shows that when you're born, your brain is very, very densely connected. And you don't, as a teen, even acquire the ability to really contemplate the consequences of your actions until you start to have functional decomposition and segregation of the different functional units of the brain that allow you to have all of the different aspects of synthesizing the multicellular, the multisensory information and being able to predict the consequences of your actions. And as much as we like to rail against our tweens, didn't you think what would happen if you failed that test and you couldn't get into the school that you wanted? I mean, how many of us have had that sort of conversation with our kids? They actually do not have the machinery to be able to do it. So you can rail at them all you want. There's no function for executive function before the functional differentiation happens. it's a painful truth to a parent. You can tell I've got a 12-year-old. Is that right? So you wrestle with this, but this is not quite a joke, because the neural networks that we've built are kind of in this category. They haven't reached this level of functional decomposition yet. And so if you look at a cross-section of the actual brain and start to ask, well, what are the pieces that we've made? This is a wonderful piece of art by Greg Dunn. His name is not visible on the projector, but beautiful piece of art from an actual scan of a human brain. And you can start to look at the pieces of the work where you think of things like AlphaGo, which is kind of collecting total information about the Go games that have been played in the universe, as we would store it in our frontal cortex of what's a good game and what's a bad game. Or if you think of Watson, that's a similar collection of semantic information for solving problems like Jeopardy or chess matches and so on. With Deep Blue, or Alexa, which is equivalent to some portions of our auditory cortex to sample sound and make decisions and representations of what sorts of communications we're receiving, or the convolutional networks that operate in systems like Google Photos that identify the faces in your photographic library. So we've made systems that operate on the different parts of the brain, but we haven't composed all of them into the synthesis of all the things that we use to represent more complicated abstractions. And so we haven't really represented a complete distribution of active thought. Now, there have been graph representations of knowledge in semantic systems, but not ones that reliably mimicked what a human actually did. And finally, there's this issue of the integration and synthesis of the information, where you start to think of how do you take all of the memories, the vision, the sound, the audio, and not just correlate what's happening at the same time, but preserve the information from the different sensory channels in such a way that you do the computations. So, people like DeepMind, they're beginning to look at this idea of this agglomeration in the hippocampus, this kind of switching network of the brain, and they're starting to build versions of that simple hippocampus that does that sensory fusion work. But there's another piece that's also received scant attention, which is the cerebellum. And this is a really interesting part of the brain, because this is what we thought for many years as neuroscientists. Me at Caltech, going through that early neuroscience kind of canon 20, 30 years ago, really we've known for a long time that it was about muscle memory and sequences, timing sequences. You build the muscle memory by practicing. It kind of resides is trained in your cerebellum, and over time you can ride your bike without having to concentrate it on anymore. And so that's what we thought the cerebellum was about. But when we started to do the more advanced tractography analysis, and we could see how it was coupled to the hippocampus and the switching station, we realized a couple of important questions that I think we should have twigged to earlier. One, of course, is that there's more neurons in the cerebellum than the entire rest of the cortex. So if all it was doing was muscle memory, why is it so metabolically expensive? But when we looked at the tractography and said, well, that's not just connected to the motor cortex parts of the brain up here, it's connected to the entirety of the cortex. And so we realized that this idea of sequencing was completely embedded across all of your cognitive functions. And there's a couple teasers that pointed us that it wasn't just sequence generation and memorization. The even more important component was anticipation and future projection, future estimation. And it turns out you're going to hear a talk later by Jamu on concussion detection, which relies on predictions that are coming from the cerebellum and breaking because they don't get to reconciled in the cortex properly. But our senses are too slow in terms of neuron speed, right? Millisecond resolution action potentials, for us to operate in the real world. It's kind of a profound realization. You actually need to generate an expectation of what the real world will be. That's what you compute on, and it's your future estimation that generates all of your control motivations. But it's operating in all of you right now. Everything that is coming, you can predict. What is the next word that's going to come out of my... Thank you. Okay? I didn't have to tell you. You knew it was coming. That is a predictive ability that's built into your brain, fundamentally guided, we believe, by the cerebellum. But who has built an artificial cerebellum that sits external to all of the networks to coordinate them and optimize their function. We stumble on this completely kind of accidentally and ad hoc in some of the motor control work, where we couldn't get the prosthetic drive from neural control to work until we had the future predictive component. And we didn't really think of it in terms of cerebellum. We just said, yeah, just build a controller. You want a PID controller. You want to estimate what the future state is from prior. So we're thinking about it from a mathematics and control perspective, but not from an anatomical and architecture perspective, and what it means to have it as a separate subsystem. Now, so let's go through those three ideas. The abstract representation of activity. This is fabulous work by Jack Gallant's lab in Berkeley. I'm actually going to visit him tomorrow morning, where they have taken a super high resolution fMRI machine and they have linked it to a synchronized reading, where this is just a patient that's in the machine and someone is reading to them. And they're timing and synchronizing the auditory stimulus of the book being read to them with the activity in the brain. And after doing that, they actually can make a semantic map of how all of these different abstractions are represented across the brain. Similar work has been done at CMU in Marcel Just's group, where they were looking at doing the same sort of reading and sampling, and they could identify the different areas in the brain, and they were able to find 60 different locations. So they're just mapped out here in this graph, and it represents things like feelings, actions that you take and control with your body, places and locations, people that you're near. It also has another set of dimensions around emotions and governance and control. But the point is that from all of that stimulus and all of this semantic mapping, they now have a system where they can completely and with very, very high accuracy disambiguate over 60,000 not clear sensory things that we see in front of us, but complicated abstractions: benefit, fear, harm, enemy, anger. And we can now show you exactly what the topology of that activity is in the brain to represent all of these things. And so this is the sort of thing that we are looking to exploit, to say, all right, well, why don't we build these types of systems, and instead of just making an arbitrary ad hoc representation of graph knowledge, make one that mimics exactly how the humans do it, and not just from a structure point of view, but from a dynamics point of view. How does it change? And in fact, your topology, what we're finding, might be slightly different than my topology, but they're homologous. In other words, there's common structure, even though some of the precision connections might be different. But this is a profound idea. So, at Cortical, we've chosen 3 areas of focus. The first is to improve the sensory fusion and that representation of all those abstractions in a more anthropomorphic architecture. We're looking to build an artificial cerebellum, so effectively we have a future estimation coprocessor which can improve and enhance all of these functions, but importantly, with an anticipated future state that you can modulate and regulate and make comparisons and choices between. So analogous to some of the work that DeepMind has been doing in the models and the imagination direction, but a little more rooted in what some of the actual cerebellum circuitry is doing. And so we've really chosen these 3 problems for a very important reason. And there's a few other lessons that have come to us from the neural work, and we can have a longer conversation about things like temporal codes and information theory and processing efficiency and metabolic support and so on. But these 3, synthesizing the context and the representation across many domains, embodying abstractions in a system that is much more anthropomorphic, and being able to estimate future consequences, because we believe that these are the roots, the fundamental roots, that give you the most impact and the most computability for value judgments and human representative ethics. And it's kind of an interesting idea to think that now we could begin to have systems which quantify how do humans really represent ethics. And we can start to tune systems to represent particular people's ethics and kind of draw boundaries of what's acceptable behavior and what's not. And start to develop systems of representation that are analogous to how humans make these decisions, so that we can have real conversations instead of saying, well, this is our matrix of 75,000 free parameters that explain the ethics of this decision. So you start thinking this way and you realize, well, you know, I could certainly tune my Barack Obama ethical engine and my Donald Trump ethical engine and say, where am I, in this spectrum? But, there's another important piece that we all operate with. So we have our own ethics engine. So imagine that I wanted to make a simulation of Phillip. Okay? I don't just speak with respect to what my ethics are. I consider my audience. I, in my head, am running a simulation not just of what my ethics are, but what your ethics are and how you're going to respond to me. To become socially adept, to develop emotional intelligence, I have to be expecting and acknowledging that you are different. You have different concerns, different worries. And so I am running kind of a recursive system to spawn not just my engine, but my estimation of what your engine is. So I can make digital empathy. And the bar is not that high for a first set of systems. Look at this. Look at the age. This is empathy right there. At that age. No real instruction, but real concern. So I think that this is a really important area, and one of the reasons we decided to focus on those three pillars of abstract representation, future estimation, and synthesis across broad domains is that we are on the brink of making profound societal decisions. And many people are saying, oh, okay, AI, big hype right now, but we really are at a crucial juncture. Today, it's mostly a tool. We use it to analyze things. We use it to give us information on our businesses so we can be more efficient. But we are on the very brink of giving the decision to a 1,500-pound vehicle going 50 kilometers an hour where to go by itself with no human intervention. There may not be an ethical decision every mile, but you can bet there will be some that have life and death consequences. Same is true for medical health, medical diagnostics. Do you have cancer? Do you not? What is the intervention? Automating the tools from the sensor to the feedback to the intervention. These are becoming life and death information challenges. Is there a point where we can adjudicate justice or independently drive our children to school or diagnose and treat disease for regions of the globe where there are no doctors? We are on the very brink of doing all these things. But if we can't audit and understand what it tells us, this is a very dicey proposition. And I think that the transition from tool to actor that we are on the very brink of needs to have the instrumentation where we can trust it. So our goal at Cortical really is to develop a first generation of these new tools that are more anthropomorphic. But I'm going to tease you with something that I've been thinking about and leave you with a very profound thought. I talked about things like emotion and abstraction, and we didn't really touch too much on things of, what is the core of your identity and your notion of self. But when I started to ask this question, and I've been working very, very hard on this for the last 8 months, what is the underpinning of consciousness? And I started to realize that in every case, and you could pick your favorite philosopher, your favorite scientist, I've not been able to come up with one example that did not involve the fundamental atomic element of anticipating some aspect of the future. And so I actually think that those three elements, future estimation, abstraction, and synthesis, are actually the roots of consciousness. And I haven't proven it, but I think that we could begin to build a first generation of what I would call ethical machines that start to have rudiments of consciousness. That's what we're trying to do at Cortical. Now, for those of you that think that that's a little bit high and mighty, I'll just close with a humorous quote from my old thesis advisor, Marvin Minsky, long renowned as one of the founders of artificial intelligence. And the point is that we shouldn't take ourselves too seriously here. And his point is a good one, because this notion of, can we make an auditable AI? We'd clearly like to do a better job, but frankly, I can't even figure out why my accountant makes decisions. And he certainly can't explain his internal cognitive processes. So be careful of asking your computers to do what even humans can't do in the kind of emotional recognition and decision boundaries. But anyway, I think that this is a fun thing to aspire to. Thank you very much. Yes? Yeah, that's a very keen observation. And I would follow to say the beauty of systems like this is we can spawn 1,000 of them and tune each of them to adapt and mimic what the different cultures represent. And so now you can imagine kind of ethics engines which will say, here's the information we have, here's the decision you're making, here's how 500 other people would decide from different cultures, where do you want to be on the spectrum? Yeah, and then you've got all sorts of genetic evolution experimentation fun to apply, right? That's right. Yeah.
Yeah, you seem to have invoked an idea of outcomes and outputs and functionality to what artificial intelligence is. I mean, built at the end of the idea of artificial intelligence, as you described it, is the ability to autonomously drive a car or autonomously make ethical decisions or do something. It seems as if this is very value-driven intrinsically to get to that point because you have to have those metrics to decide what artificial intelligence actually is, what it's doing, and what it means. Can you differentiate artificial intelligence at its core from outputs and outcomes separately or not?
I would make the distinction between a physical system that exhibits a behavior and the substrate within it that makes all the functional decisions from sensory input to motor actuation that affects the decision. And what I would argue is that what I'm trying to do is build an artificial system that is on a computational substrate that we can manufacture and operate and program and control that will do things as close as possible to how humans behave. And you think of the Turing test at its extreme limit, and I'm not suggesting that that's the best measure. But I think to your point, it's artificial in the sense that it's not a biologically evolved organism. Other than that, I think we're kind of going to get caught in semantics. Fair point? We can talk more later. I'd love to engage in that. Yes? We have, and when you start to think of consciousness at the atomic level like that, you start to realize that you can take abstract extremes and say, even a paramecium in the ocean that has light sensors and will orient itself towards the sun when the sun is out, and so that it rises and then it sinks at night. All of those things are biological anticipations of what's evolutionarily advantaged. And so in that sense, you could say that's a very tiny rudiment of consciousness where it is predicting the evolutionary consequence, its genetic heritage, propagation, and so on, of what is advantageous to it. Now, we have much more complicated systems to do that, which employ, much more computational resources, billions of neurons instead of, hundreds, in even the most elementary, tiny organisms. So we can predict much farther into the future and many more alternatives with many greater influences and sensory inputs. But I don't think that there's anything more complicated than taking those inputs and anticipating potential futures. Now, what's really interesting about having the cerebellum as an external unit is that it allows you to have an API that accesses all of the sensorium as opposed to one specific computational function where it might be embedded. And let me highlight that is very, very important to be able to synthesize all of the different diverse information sources to make predictive actions. The other thing that it comes with is the ability to direct attention, so that now not only can you predict the future, but with conscious will, you can affect which future you're concentrating on and imagining. So those are two very powerful features that you could imagine building a predictive engine to start biasing and checking and so on from those type of integrated information streams. Okay. Thanks, Lisa.
Thanks, Scott.